Hi, we're Group 2B, and in this presentation we'll be walking you through our Furi proposal titled Inhibition of Bacterial Biofilm Formation by Chitosan and Algae Under Electricity and UV Light. The research question that we're addressing here is how the addition of polymers like chitosan and algae prevent reformation of antibiotic-resistant bacterial biofilms under the effect of electricity and UV light. Our hypothesis is that the electrostatic field and UV, in addition to chitosan and alginate, will enhance degradation of antibiotic-resistant bacterial biofilms.
Okay, so now we will discuss some basic background information to help explain the experiment we have at hand. We will first talk about what bacterial biofilms are and the challenges that occur because of them. So to start off, bacterial biofilms are groups of bacteria that attach to surfaces and they are sheathed by a protective matrix which helps bacteria to resist both antibiotics as well as environmental changes. The growth of biofilms in regards to infections specifically is very challenging as bacteria within these biofilms are more resistant to antibiotics as the protective matrix that I mentioned previously shield medications from reaching the bacteria or an infection that's being treated, prolonging recovery time and how effective medications are at treating such infection. And we will also discuss the background of our two natural polymers that we have hypothesized will be efficient in enhancing degradation of antibiotic-resistant biofilms. So the first one is going to be chitosan. Chitosan is a biopolymer containing antimicrobial properties which will help to disrupt bacterial cell membranes, preventing adhesion of bacteria. And then we also have the polymer fungi. And fungi is going to be a eukaryotic organism that is going to provide bioactive compounds which disrupt cell functions of bacteria. So that alone will help to reduce possible bacterial colonization, which basically is, helping to prevent more spread of bacteria. The growth of biofilms created a grave challenge in treating infections. And we will dive into that a bit. So antibiotic-resistant biofilms create a massive public health threat, with biofilms making infections, one, difficult to treat, which heightens the chance of recurrent infections, two, raises the chance of spreading resistant bacteria. And to kind of close it out with point 3, these biofilms have the ability to cause chronic illnesses with these resistive bacteria. So that is kind of the main background points of this. And it is also important to note, as we will discuss further, that these bacterial biofilms are often found on medical devices, which creates not only a burden on patients, but as well a burden on healthcare systems.
Our components are chitosan, sodium alginate, staphylococcus, electrostatic field, bacterial biofilm, and UV light. We would use crystal violet assay and live dead staining as well. We would culture antibiotic-resistant bacterial strains, specifically staphylococcus, and would treat the biofilms with solutions of natural polymers, and in this case chitosan and alginate. These polymers were selected for their biofilm disrupting properties. To enhance the treatment, we would expose the biofilms to UV light and an electrostatic field. After this treatment, we would evaluate the degradation using live dead staining to evaluate bacterial viability, and we would use crystal violet assay to quantify absorbance. Innovations. We use similar features as are commonly used, like UV light and electrostatic fields. This targets biofilm degradation through physical and chemical disruption. Key differences, however, include our natural polymer integration, because of these biodegradable and biocompatible materials aren't commonly used. Dual modality treatment. This combines electrostatic fields and UV light, which isn't commonly combined. Targeted anti-biofilm action exploits the electrostatic property of natural polymers under UV light for enhanced bacterial susceptibility. Wire design is superior. Polymers like chitosan directly interact with bacterial EPS, weakening biofilm integrity. UV light amplifies polymer effectiveness, exposing bacteria, preventing biofilm reformation. Surface modification by chitosan prevents bacterial adhesion, and the sustained release of antimicrobial agents from alginate slows down biofilm regrowth. Using biodegradable natural polymers, this minimizes the environmental impact. This modular design allows for adaptation in different applications, like medical devices and water systems.
Hi everyone, let's look at the challenges of our approach. We'll go over 3 challenges we have. The first one will be the electrostatics field application. Second will be cost and resource requirement. Third one will be the heterogeneity of biofilms. So for the first one, it can be very hard to apply the electricity field evenly on the rough surface. This can take the treatment less effective in some areas. For the second challenge, we have the cost and resource requirements. Using this method on a large scale, that may be very expensive, and it needs specific equipment like UV lamps and high quality materials. For the third challenge, we have the heterogeneity of biofilms. So as we know, like biofilms are not all the same. They are like different types, may react differently, and these methods may not work quite like equally for all. So those limitations are important to improve as we continue our research. To summarize, here's what we have discussed. I'll start with innovative approach. So in our methods we used Chitosan, alginate, UV light, and electrostatics field to target antibiotic-resistant biofilms. We also went over the key advantage. It can break biofilms more effectively and stop them from coming back using natural biodegradable materials. We also went the potential challenges we have, so cost and uneven treatment of the challenges that needs more research, typically. And then lastly, the future application that this method could be held. So this method could help in medical devices, water treatment, and other applications. And thank you for listening.
Sam, Matt, Allah, and I worked on this presentation together. Here is a breakdown of our contributions. We thank you for your time in watching our presentation. These are our references, and we're happy to answer any questions.